Bismillahirrahmanirrahim. Assalamualaikum and very good morning. Okay, so today we are going to continue with the network analysis, the transmission line analysis by using a Smith chart. Okay, as usual, please scan the QR code for the attendance. Okay, now we are going to look at how we can use a Smith chart to visualize or to estimate the matching between the load and also the characteristic impedance. Okay, for example, look at this setup. So you can see a Smith chart from the display of the vector network analyzer. So this is basically the load. Okay, you can represent this as the transmission line. The black cable is the transmission line. Okay, terminated by a load. So this is the load. So you have the ZL. Okay, and this is the input or the generator in which you have the Zin. Okay, so in the transmission line you have the characteristic impedance. So it is a Z0. So if you still remember that a system is matched when the Z0 is equal to ZL. So by using this Smith chart, you can look at the performance of the transmission line or the system. So you can see whether the load is matched to the characteristic impedance of the transmission line. Okay, so let's recall back the transmission line circuit. So you have a transmission line and you have your load and you have the characteristic impedance in the middle, in between the transmission line, and then you have the Zin. Alright, so so you also know that the reflection coefficient equal to ZL minus Z0 divided by ZL plus Z0. And the reflection coefficient will be 0 if the system is matched, in which Z0 equal to ZL. Right, so by using a transmission line, you can estimate what are the VSWR, the reflection coefficient, and other parameters without the need of performing calculation. Right, from the Smith chart itself, you can estimate what are the value for each parameters so that you can estimate the performance of the overall transmission line. So basically, the impedance, the Z is equal to the real part plus the imaginary part. So we need to find the real part and the imaginary part from the Smith chart. So from here, then you can get your VSWR. You can also get your reflection coefficient, and you can estimate the length as well for the transmission line. So a quick overview on a Smith chart is basically a graphical aid that will be very useful for solving transmission line without the need of complicated calculation. So it based on a polar plot of the voltage reflection coefficient, and it can be represented as this equation in which you have the magnitude, the real part, and also the imaginary part. And a Smith chart provides a useful of visualizing transmission line without the need of calculation, as I mentioned earlier. And a microwave engineer can develop a good intuition or overview about the transmission line and also impedance matching by looking at looking at this Smith chart. Okay, usually used to solve the impedance at any point on a transmission line when the load is known. Okay, all impedance on Smith chart are normalized to characteristic impedance. Okay, in practical, we can assume the characteristic impedance equal to 50 ohm if the value is not given, or sometimes it can be 75 ohm as well. Okay, but usually 50 ohm will be used as the characteristic impedance of the transmission line, so that the load impedance is approximate to match to the well matched to the system if it is close to Z0 equal to 50 ohm. Alright, so before we begin, so please download and have a printed copy of a Smith chart in hand. Okay, so you need to plot all values onto the Smith chart, and you need to practice a lot because you are about to have you need to do the same for the test and final exam. Right, so just a quick recap on the reflection coefficient, in which from the Smith charts, once you know the impedance, the normalized impedance, then you can estimate the reflection coefficient. So this is the reflection coefficient equation that you have learned earlier. So when the Z0 equal to ZL, so you know the system is matched. So the reflection coefficient will be 0. So there's no reflected wave, and all the maximum power or all signal being transmitted to the load. But if the reflection coefficient equal to 1, so there will be completely reflection on the system, so no power is delivered to the load. Alright, so from the Smith chart, when the system is matched, so you'll see a point here representing reflection coefficient equal to 0, in which the normalized impedance of the system is completely matched. And from the scale, so I'll show you what basically being represented by the horizontal lines, and what are the curve on the left and on the on top and at the bottom, and what are the scales down there. Okay, there are basically three types of Smith chart, but we are going to focus on the Z chart, in which we have the circle line and also the impedance, the reactance lines on top and at the bottom. All right, so if you have the Y chart is basically the admittance, representing the admittance, and Z representing the impedance, and another one, the more complicated chart, basically combines both the impedance and also admittance on the same paper or on the same chart. Okay, let's look at the components included on a Smith chart. So the first one is the circular lines. Okay, that's basically representing the resistance circle, or the normalized resistance or normalized impedance. Okay, so you can see these lines. Okay, and you can see the value represented by each lines. Okay, for example, here is 5.0 when the normalized impedance is 5.0. So remember, Z normalized impedance equal to the R plus JX. So the normalized R here is represented by the circular lines. Alright, so this one, okay, up to this point is 1.0, and here is 0.0, 0.2, 0.3, 0.4, okay, and etc. And the last point is 0. Okay, while on the top and at the bottom, you can see the reactance lines. Okay, from this here up to upwards. Okay, this representing the reactance value. All right, so you can see it's 2.0, 3.0, and then 1.0. Okay, and on top it represents the positive J X, while at the bottom representing the negative GX, okay, and etc. Okay, all right, so for example here is 2.0, so it's positive J2. Okay, at the bottom here is negative J2. Okay, so this slide summarizes the components on a Smith chart. So the outer line representing the real value of normalized impedance equal to 0. Okay, so at this point it represents the red lines here representing when the real impedance, normalized impedance equal to 1. Okay, the circle value here is 1.0. So it's a match point where you know that the normalized impedance equal to your ZL divided by Z0. So we assume Z0 equal to 50. So when it is matched, so ZL equal to Z0. Therefore, the normalized impedance at this point is 1.0. So from 1.0, so you have a line crossing at 1.0. Okay, so as I mentioned, it is a matched system. So when ZL equal to Z0. So and again, the value represented at this point is the normalized impedance. Okay, so at this point there's no imaginary values, J equal to X equal to 0. Okay, and on the far right representing the open circuit. Okay, if you still remember the open circuit, so your ZL equal to infinity. So here is your Zin, and in the middle is Z0. So when ZL equal to infinity, so the normalized impedance equal to infinity. All right, so the impedance is placed at the far end of the system, and again when the point lies on the horizontal line, that's basically the imaginary part is 0. Okay, on the far left, basically representing the short circuit. So when you have your ZL equal to 0, so the normalized impedance for short circuit equal to 0. And again, when the point lies on the blue lines on the horizontal line, the imaginary part is 0. Now let's look at the simplest part of plotting on a Smith chart. So first, plotting the ZL, the load impedance, on a Smith chart. So the steps are: first, normalize the impedance value by the Z0, by the characteristic impedance. So if you have your ZL, for example, equal to, given your ZL equal to, for example, 100 plus G50, for example. So when you normalize, it becomes ZL prime equal to 100 divided by 50. So assuming that the Z0 equal to 50 ohm. So plus G, so you need to normalize both the real and imaginary part by the same Z0 value. So your normalized impedance equal to 2 plus J1. Right, next, once you have this value, this equation, then you find the real impedance part on the chart. Okay, so along the lines, find where is ZL equal to 2, for example, is here. So this is the lines and ZL equal to 2. And next step is find normalized imaginary part. So the normalized imaginary part is 1. So refer to the crossing, so J positive, so it will be on top, positive J on top. So 1 is, here is 1.2, so 1 somewhere here. So this is the lines for J1. Next, plot the intersection on chart. Okay, let's look at an example how to plot the ZL on a Smith chart. So example A. So given the ZL equal to 50 plus J50. So to plot the load impedance into the Smith chart. So the first step, you need to find the normalized impedance. So you need to divide the ZL by the Z0. So assuming that the Z0 equal to 50 ohm. So your ZL equal to 50 divided by 50 plus J50 divided by 50. So your normalized impedance equal to 1 plus J1. So the next step is find the 1 on chart. So refer to the circular line. So 1 is somewhere here, so it's here. So this is the line for real part 1. Okay, next, the third one, find J1 from the chart. So positive J will be on top, so negative J will be at the bottom. So positive J1, so here is 1.2, so here is 1. Okay, so this is the J1. So the first step is plot the cross section between these lines. So the cross section is here. So you can put A. So this is where the ZL lies on the Smith chart. Okay, let's look at example B. So you have the ZL equal to 300 minus J25 ohm. So again, the first step, you need to find the normalized ZL equal to 300 divided by 50 minus J25 divided by 50. So you got 6 minus J0.5. So the third step is the second step, find 6 line on the Smith chart. So 6, 3, 4, 5. Here is 10, so 6 somewhere here. Okay, so 6. And then find negative J 0.5. negative j 0.5. So negative j will be at the bottom. So 0.5 is somewhere 765 is here. So these lines, okay, you can see the same number here as well. So find the crossing somewhere there. Alright, so the fourth step is plot the cross section. Alright, so maybe here, and you can label it as B. Okay, so as simple as that. So your value is the point for normalized impedance is at that point A and B. Okay, next we are about to determine the VSWR from a Smith chart. So the first step is to plot the normalized ZL. So normalized ZL. So once you have the ZL, remember you need to find the normalized ZL. So you need to divide the real and imaginary part by the Z0. So the example, let's have your ZL equal to 100 minus J100 ohm. So again, your ZL bar equal to 100 divided by Z0, assuming that your Z0, the characteristic impedance, equal to 50 ohm. So 50 minus J 100 divided by 50. So your ZL equal to 2 minus J2. Okay, so you plot this point onto the Smith chart. Next, you draw a circle from the center of the Smith chart. That's representing the VSWR circle. So please get ready with the compass and protector. So it'll be good to estimate the circle by using the compass protector. Next, watch out for the VSWR value from the Smith chart. Okay, let's look at an example. Before that, to determine VSWR, so you need to draw a circle. Please get ready with your compass protector. Okay, let's look at the example A. So given the ZL equal to 100 minus J100. So in all cases, we assume Z0 equal to 50 ohm. Okay, so the first step is to find ZL prime and plot on the Smith chart. So divide by Z0 minus J100 divided by Z0 equal to 2 minus J2. Right, plot this point onto the Smith chart. So it's 2 here minus J2, so it will be at the bottom. Where is your J2? 1.2, 2.0 is here. Okay, then you have point A. Okay, so I can remove these lines to avoid confusion. Alright, next, to find the VSWR, draw a circle surrounding from the center. So this is the center. So you use your compass protector and draw a circle from the center up to point A. So you get this line. So the value of the VSWR is the one crossing the horizontal lines somewhere here. So it's 4 point, here is 5, so it's 4.245 maybe 6. Okay, so about 4.6. So for the first case, the VSWR equal to 4.6 to the ratio of 1. Okay, so this is the first VSWR of A. So VSWR for A, point A. Okay, let's look at another example. Example B. So given the ZL equal to 50 plus J100 ohm. So the first step to find VSWR, find and plot the Z, the normalized Z. So 50 divided by Z0 plus J100 divided by Z0, 1 plus J2. Okay, plot the point onto the Smith chart. So it's 1, so here, and it's positive J on top. Positive J2, so here. So the point B is here, the cross section. Okay, so then I can remove this one to avoid confusion. Right, next is to draw a circle from the center. Again, the center is here. Draw a circle from the center to point B. Right, so you should get this approximately. Okay, so the cross section represents the VSWR somewhere here. So here is 5, here is 10, so 6, 7, 8, 9. So here is around 5.5. Okay, so for VSWR for point B equal to 5.5 to 1. Okay, to 1. The reference point is here, the center of the Smith chart. Okay, let's try another one. C. So given your ZL equal to 50 ohm, so find the ZL and plot the normalized one. So 50 over 50 equal to 1 plus J0. Okay, so since there's no imaginary part, next plot the point onto the Smith chart. It's 1. Okay, so 1, J0 is along this line. So point C is here. Okay, next, draw the circle from the center. So circle from the center with radius 0. It's here. So the circle crossing at point 1. So VSWR C equal to 1 to 1. Okay, so in this case, when it is at the center, so the system is completely matched. Okay, next we are going to look at how to determine the reflection coefficient from a Smith chart. Right, so in order to get the reflection coefficient, so you need to use the scale, okay, that included in at the bottom of the Smith chart or underneath the Smith chart, and there are few parameters, parameter scale at the bottom. So you need to find the reflection coefficient bar, scale bar. Right, so the first step is to plot the normalized impedance. So get your Z and plot it on chart, for example here. Okay, and then draw VSWR circle from the center. Remember the center is there. So draw a circle using your compass protector from the center, something like that. Okay, and then measure the radius using ruler. Then you need to use ruler. So measure the radius from the center, okay, to that circle, and then use the same size, okay, the same radius, I would say R, bring it down here and place it on top of your reflection coefficient scale. So I suppose somewhere here, this is from center, so because we are measuring from center, so reflection coefficient somewhere here, so place the same radius R here, okay, right? So for example, from center, so this is the reflection coefficient bar, this one, okay, so place the same radius R onto the scale, for example here, okay, the same R, then you'll get exactly the magnitude of your reflection coefficient there. Okay, magnitude of your reflection coefficient. For example, in this one is 0.424, 0.44. Okay. The next, determine the angle from the sidebar. Okay, from the Smith chart, then you'll notice there's another row, another parameter on the sidebar. So look at the angle of reflection coefficient. Oops, angle of reflection coefficient in degrees. Okay, and read through the points. For example, if your Z just now here, the normalized impedance there, so draw a line from the center crossing the Z, then read through the angle there. Okay, for example, here underneath is negative theta and on top is positive theta. For example, here from the center, so it's crossing there, so the degree is somewhere here. Right here is 20, so maybe here is 10, so here is maybe negative 8 degree. Okay, so you'll get your reflection coefficient equal to the magnitude of your reflection coefficient and the theta in degree. Or you can also represent it as magnitude of your reflection coefficient, EJ theta. Okay, let's look at an example to determine the reflection coefficient. Reflection coefficient for an impedance of 200 minus J50 ohm. Okay, so the first step, determine the impedance and plot it. So you need to divide by Z0, so assume Z0 equal to 50 ohm. So the normalized value of the impedance is 200 divided by 50 minus J50 divided by 50 equal to 4 minus J1. So you need to plot it on the Smith chart, the impedance point, the normalized impedance point. So it's somewhere 3, 4, somewhere here, and crossing at 1, these lines. Okay, so it's there. Okay, then I'll remove the crossing. Okay, that's the impedance point. So normalize ZL or ZL. And then second, you need to draw VSWR line. or you can also determine the VSWR value from the center. Okay, remember the center is here, so draw a circle. Okay, so you can determine the VSWR value equal to what? Okay, the VSWR is there. Okay, it's 4 point something. And then the third one, measure the radius. Okay, use a ruler, measure the radius from the center, R. Next, bring the same R to the scale. Okay, measure the R, then bring the same R to the scale of reflection coefficient. So read through the R value. So it's 0.64. So your magnitude of reflection coefficient equal to 0.64. Okay, next, draw the angle lines, okay, from the center, crossing the impedance point, and read through the angle point there. Okay, I suppose that the angle will be around -7 or -8 degree. Okay, so then you can get your final answer. The reflection coefficient equal to 0.64 with the angle of -7 degree. Okay, that's the end for the Smith chart part 1. So I'll continue part 2 in the next video. Thank you.